of clean energy systems. Following the presentation, we'll have a live Q&A with AJ. You can submit questions at any time during the session using the chat box that's over on the right-hand side of your screen. Additionally, the presentation slides will be available near the end of the session from the Handouts tab, so keep an eye out for that link. Thank you so much for joining, and with that, I'll hand it off to AJ for the presentation.
Welcome and thank you for joining us today to discuss current sensing in battery energy storage systems. For today's presentation, I'll start with a quick introduction on Onwell, then provide an overview on different current sensing technologies that exist today. I'm introducing what you need to know when evaluating these different technologies. Then I will discuss the role of current sensing in battery energy storage systems. This would ultimately lead us to what to consider when selecting a current sensor in your battery energy storage system application. Then lastly, we will review some current sensor options that Onwell offers. You may ask yourself, why are we spending so much time discussing battery energy storage systems today? It's important to know that the battery energy storage system market is expanding rapidly due to increasing demand for renewable energy integration, data center support, grid stabilization, and effective energy management. With the rise in battery energy storage systems, ensuring system safety and reliability is paramount, and current sensors play an essential role in achieving this. As we see an increased adoption in artificial intelligence technology as well, we expect that will even further fuel the demand for battery energy storage systems. So it's very important that we take us some time to talk about current sensors that are used in this application to ensure system performance as well as reliability and safety. So first of all, I'll start with a quick introduction on Onwell. Onwell is an industrial conglomerate, and we create value for customers across different industries, from aerospace to building automation, to energy and sustainability solutions and industrial automation. You know, some people think Onwell plays only with thermostats, or we provide or manufacture only thermostats. I'm happy to change that point of view today by, again, restating that we are an industrial conglomerate and we play in different industries, helping customers creating value for customers, allowing them grow both their top line as well as their bottom line. So for my team, we fall under the industrial automation strategic business group, and we primarily focus on providing solutions to support our customers to help them deliver results with enhanced productivity and safety. Essentially, our products help customers increase productivity, which benefits for them from the bottom line, as well as productivity they can share with their customers. So that's the top line as well as enhanced safety. We pride ourselves in making sure that people can come to work and return home to their families without any incidents or safety incidents. So Onwell overall for industrial automation, we are primarily focused on productivity as well as enhancing safety. So with that said, I'm going to transition now to the topic at hand here, which is current sensors. So there are several current sensing technologies, and this can be grouped into two primary groups. One is the inline, non-isolated, intrusive current sensing technology. The common technology that most people are familiar with in that space is Shun technologies, which uses or follows the principle of Ohm's law. And Ohm's law states that the voltage across a conductor is directly proportional to the current flowing through it, provided all physical conditions and temperatures remain constant. So essentially, you're measuring the voltage drop across the conductor, in this case, a resistor, and using that proportional measurement to determine the amount of current flowing through the conductor. On the other hand, you have the non-contact isolated current sensors, and this follows the principles of Ampere's law, which states that the magnetic field in space around a conductor is proportional to the electric current through that conductor. There are several options for non-contact technology, and the common ones people are familiar with is, you have the current transformer, Rogalski coil, you have All effect principle, you have AMR and flux gate. And you can really group this further depending on what you're trying to measure. If you are interested in measuring AC current, then you lean more towards current transformers and Rogalski coil. But if you're looking to measure both AC and DC current, then you lean more towards All effect, AMR, and flux gate. Again, the difference between the two groups, that's the non-contact um, isolated current sensors, indirect current measuring, and the other group, which is the non-isolated, direct inline intrusive current sensing, is the fact that the non-contact is installed such that it has no parasitic effect on the path of current flow versus the shunt current sensor that has a parasitic effect on the path of current flow. So the six options have been outlined below. You have a shunt that uses a resistor placed in series with the current placed in series with a socket to measure the current by detecting voltage drop. You have current transformer, you have Rogalski coil, you have All effect, AMR, and flux gates. Okay. Um, then just double clicking here on the All effect technology. All effect occurs when an electrical current flows through a conductor. It generates a magnetic field around the conductor, and the strength of the magnetic field around the conductor is directly proportional to the current flowing through the conductor. So as current is flowing through the conductor, a magnetic field is generated around it, and the intensity of the magnetic field is directly proportional to the current flowing. Now, you use an All effect sensor that is placed in proximity to the conductor to be able to measure or determine the intensity of the magnetic field around the conductor. And the All effect sensor, is typically orientated such that it detects the magnetic field, which then generates a All voltage. The All voltage here is proportional to the current in the conductor and provides an indirect measurement of the current. So you can see the chain effects there. You have the current flowing through the conductor generates a magnetic field. A All effect is placed close to the conductor to detect the magnetic field, and which then translates to a All voltage that is proportional to the current that is flowing through the conductor. Hopefully that is simple enough for you to understand. There are two types of All effect current sensors. You have the open loop All effect and you have the closed loop All effect. The open loop All effect is what I've just explained now, just using an All effect sensor to generate the All voltage and measuring the All voltage, which is directly proportional to the current flowing through the conductor. While the closed loop uses a compensation technique where the All effect sensor detects the magnetic field generated by the current sensor, then uses a feedback system. The secondary coil generates a magnetic field which is in the opposite direction to cancel out the field initially produced by the current. The amount of current needed to generate this canceling field is then measured, and that value is proportional to the primary current. So in other words, in the open loop, it's a one-directional system, while the closed loop has a feedback system, has a counter secondary secondary coil that generates another magnetic field, so cancel out the primary magnetic field and improves the accuracy because of this feedback system. Both open loop and All effect are isolated current measurement, indirect current measurement, and the All effect has some advantages. The closed loop All effect has some advantages over the open loop All effect. One is overall it delivers a higher accuracy and better linearity because of the internal compensation and the nulling of the magnetic field. You have a faster response time. You have a reduced temperature drift, and you have just it's more suitable for high current measurement. And then using those two as reference points there, I'm going to just touch on two different current sensors that Honeywell offers that are isolated current sensors based on All effect technology. The CSSV series is an open loop all effect current sensor. It's bidirectional. It varies or ranges from 100 amps to 1500 amps. The output type is voltage, which allows you deliver or allows us to deliver a response time of 6 microseconds. The accuracy for the CSHV series is 2%, while the CSNV500 series is a closed loop all effect. The sensing range here is bidirectional 500 amps. Output type is CAN communication, and the total accuracy is 0.5%. So now when you compare the open loop CSHV series to the closed loop all effect CSNV500 series, one thing that stands out to you there is the difference in the accuracy. And the open loop accuracy is around 2%, while the closed loop all effect accuracy is 0.5%. So again, you start seeing the benefits of open loop versus, or the difference between the open loop versus closed loop when you consider the accuracies of both sensors. So remember, we touched on the shunt technology as a direct, intrusive, inline current sensor that uses Ohm's law, measuring the voltage drop that is directly proportional to the current flowing through the conductor. Um, how does the shunt technology work? It operates by measuring the voltage drop across the precision resistor that is placed in the path of the current flow. So this is placed directly in the path of the current flow. It is intrusive, which could be parasitic as well because of the loss in the line as well as the heat generated, all translating back to a parasitic element of the sensor. Now, from a current measurement standpoint, what we've seen is that shunt technology has good accuracy in the lower amperage range of less than 300 amps. When you get above 300 amps with shunt technology, then you start seeing some inaccuracies or inefficiencies, and also has a bigger impact on your overall circuit because then you have a bigger loss on your line. You have a bigger loss, voltage drop, and heat dissipation and heat generated, which could have an effect on your overall system reliability and create some safety concerns. However, for the all effect sensor, which is isolated and an indirect current measurement technique, it has a better accuracy across a higher sensing range, up to 1000 amps and even beyond. It is more suitable for systems where you're going to measure above 300 amps because you're able to still get the 0.5% accuracy across the range. It has better temperature stability as well because you do not have the heat generated by shunt resistors, and you have a compensation algorithm typically in your all effect sensors that allows you deliver stable accuracy across the sensing range. So when you consider all of that, you see that when you consider shunt versus all effect, the all effect is a better solution for measuring current at higher amperage. So just deep diving into the shunt versus all effect to provide you a more holistic view on the difference between both. So shunt current sensors or shunt technology works with both DC and AC currents. All effect as well works with both AC and DC currents. The shunt sensors have no inherent isolation in their configuration, so it requires some extra circuitry at the system level to provide that isolation. Unlike all effect sensors that has an inherent electrical isolation, so because of this indirect current measurement technique or approach, you have complete isolation from the primary um, electrical part or electric current flow or electric current part. Shunt sensors could be simple as well because it's a simple shunt resistor with bus bar mounting. Um, However, you still need to worry about the isolation circuit for safety. While for all effect sensors, it's simple with built-in isolation, no need for additional circuitry. You could have bus bar mounting as well too for the all effect sensors. So from a simplicity standpoint, you can rate both of them to have similar simplicity. For accuracy, like I said earlier, from 0 to 300 amps, you have good accuracy with shunt sensors, and above that, you have um, some some concerns around the accuracy. Compared to all effect sensors, you have overall better accuracy even in high current applications of up to 1,000 amps, 1,500 amps, even to 2,000 amps if needed. Linearity. All effect sensors provide better linearity across a wide range. Shunt technology provides good linearity in low to medium current ranges. That's again to around 300 amps. Heat dissipation. This is one of the shortcomings of shunt technology. Because of the shunt resistor, the metallic alloy, you have heat generated at higher currents, which again could be parasitic to the socket. While for all effects, because it is completely isolated indirect current measurement, you do not have the parasitic heat generation. It's just a minimal heat generation that you get from typical electronics, but nothing significant to worry about like you would have to plan and design for shunt resistors. Again, for temperature drift, because of the metallic alloys at this higher current, you have higher drift because we all know that metals behave differently at different temperatures, so that could also have some effect on the overall current measurement or accuracy. While for all effects, it's low temperature drift, ideal for precision applications, and you typically have some compensation algorithms in your all effect sensors to take care of some of the abnormalities that you would, or some of the drifts that you might normally see due to temperature and humidity. You have a temperature compensation algorithm in your all effects that nullifies that. So overall, shunt sensors are more ideal for the lower current sensing range of 0 to 300 amps. And as you get into the higher sensing range of 500, 700, 1,000 amps, all effects are better because it provides you better accuracy, minimal heat dissipation or heat generation, and no parasitic loss to the line. Okay, so next year I'll just provide an overview here on battery energy storage systems. In your typical battery energy storage system, where you see the container, it could be a 20-foot container or 20-foot container, or even 12 or 17, depending on the different designs. What you typically have in there is a lithium-ion battery cell that is installed in the lithium-ion battery module that then goes into the storage systems. So as you will notice here, you have different compartments here. This is your lithium-ion modules. Then all together combined, it forms a rack. So you have different modules installed to form the lithium-ion battery rack, and you have a battery management system that is used for managing the operations of the different battery modules. And the current sensor is installed in the BMS. So the current sensor helps the BMS measure the current in the modules. It monitors the battery charge and health, helps with overcurrent protection, optimizes power use and extends battery life, helps with load management as well as safety compliance. So the current sensor plays a very important role in the overall operation of the lithium-ion battery racks that ultimately several of these racks make up a container or your battery energy storage systems. Now, selecting a current sensor for your battery energy storage system. Accuracy is very important in battery energy storage systems for several reasons. One is for energy management and efficiency. For your battery energy storage systems, you require a precise energy measurement that's using an accurate current sensor to essentially calculate the energy flow in and out of the battery energy storage systems. If the current is measured incorrectly, the energy stored or supplied by the battery may be inaccurately determined, leading to inefficiencies in your storage system operations, which could have some impacts as well. So accuracy is very, very important. We also want to optimize the charge and discharge cycles because the precise current sensing ensures that the battery is charged and discharged at optimal rates, enhancing the overall efficiency of the system and reducing losses. You also want to balance supply and demand, especially in grid applications. The battery energy storage systems play a critical role in balancing supply and demand. And the current sensors are inaccurate. The system might either undersupply or oversupply energy to the grid, which could lead to frequency imbalances and instability in the grid. You also want to prevent overcharging and overdischarging, and an accurate current sensor just helps you to maintain a proper state of charge and the depth of discharge. Inaccuracies can lead to overcharging or overdischarging, which degrades battery health over time and reduces its lifespan. So, so accuracy is one of the primary functions, or is a critical part of the critical consideration when you're selecting a current sensor for your battery energy storage systems, because the accuracy of the current sensors could have a significant impact. And as we talked about earlier, the current sensor for Shun technology, the accuracy is good to 300 amps. Then when you start getting above 300 amps to 500 and 1000 amps, you could have some concerns with the accuracy compared to non-contact all effect technologies, whereas really good accuracy across the entire sensing range. Okay. Now for safety, the current sensor also plays an important role in the safety of the system. So, for example, shunt resistors or shunt technologies do not provide galvanic isolation, meaning that the current sensor is not electrically separated from the high voltage socket. What does this mean? That means in a high voltage battery energy storage system application, where voltages can reach several hundreds or thousands of volts, the lack of isolation poses a significant safety risk. There is a potential for dangerous high voltage exposure in the measurement and control systems connected to the shunt, risking electrical shock, equipment damage, or system failure. When you compare this to the All effect sensor, the All effect sensors, by contrast, provide an inherent galvanic isolation because they measure the magnetic field generated by the current sensor rather than the current measurement directly, ensuring electrical separation and isolation between the measurement socket and the high voltage conductor. This is a very important element again because uniquely in the battery energy storage systems where you could have really high voltage, you want to make sure that there's electrical isolation and separation between the measure socket as well as the primary socket as well. Power dissipation and generation as well. So EMI resistance and robustness. Um, in Shun technologies are sensitive to electromagnetic interference and other forms of electrical noise, particularly in high voltage environments. This can lead to inaccuracies in the voltage measurement across the shunt. In a BESS application, that's battery energy storage system application, particularly in high power applications, the presence of switching inverters, converters, and high frequency signals can generate significant EMI. And the shunt may pick up this noise, reducing the efficiency of current measurement, especially in a dynamic environment where you have so much switching going on between for the different subsystems. Now, for all effect non-contact technology, they are less sensitive to electrical noise and provide more reliable measurements in high voltage and noisy environments, making them better suited for battery energy storage system applications. For power consumption, shunt resistors create a voltage drop that is proportional to the current, which can interfere with the system performance, especially in high voltage systems. Um, in a high voltage battery energy storage system, even a small voltage drop across the shunt can impact system efficiency. The voltage drop reduces the overall system voltage and can create inaccuracies in the current measurement, particularly in applications where precise current control or voltage control is critical. That's, for example, in grid connection or inverter control. So, for all effects, Since the Hall effect sensors do not directly introduce a voltage drop into the circuit, they offer a more accurate and efficient method of current measurement without affecting the system's operating voltage. Again, this highlights the fact that Hall effect current sensors are better suited for BESS application, and they have shunt technology or shunt resistors generate heat that could become parasitic and could create other additional safety risk or hazard versus non-contact that generates minimal heat and has no minimal risk from a system safety standpoint. So the key takeaway is that when you consider all of this, shunts are not ideal for high voltage BESS application. They lack electrical isolation. They generate heat that could become problematic for system efficiency and accuracy. They have a voltage drop impact as well that could impact performance, system performance and accuracy, especially in high voltage applications. From an accuracy standpoint, shunts can lose accuracy at high currents due to small voltage drops that are difficult to measure. They are susceptible to noise as we have different switching. They are prone to interference from EMI, which is common in high voltage environments. So with all of this, the non-contact Hall effect is more ideal for battery energy storage systems because with considering all the elements I just listed now, the non-contact Hall effect offers just a more robust and better offering overall. So we've said that accuracy is very important in current measurement in battery energy storage systems. So I'm just going to highlight, the accuracy of some of Honeywell's current sensors versus competition. So for battery management systems, we have the CSSV1500 Series, and that has different current measurement. In this test or experiment here, we looked at the accuracy of the current sensor at different temperature conditions, at ambient, at -40°C and 85°C. That's looking at the two extremes of the temperature range. And you would notice here that our advanced compensation algorithm here delivers stable performance across the temperature range and staying within the specifications of 0.5% accuracy. Our competitor in this space that has a similar non-contact Hall effect technology here has a varying profile for accuracy. And in this instance, actually, you can see the accuracy out of the specifications listed on the data sheets. So when you're thinking about a current sensor, non-contact Hall effect, the takeaway is that Honeywell's sensor provides you better accuracy across the sensing range. And in a BESS application, where accuracy is very important, you get better value for Honeywell's current sensor than a competitor. Additionally, Honeywell's current sensor has robust anti-magnetic interference that provides you more flexibility when you're designing this into your battery management systems. We require a separation or distance between the sensor of bus bar of 5 millimeters. Our competitor in this space requires 10 millimeters, which might affect your flexibility when you're designing those very complex systems. So Honeywell sensor again offers just a better value from flexibility of design, accuracy, ease of integration into your battery management system for your battery energy storage systems. I would like to highlight one of Honeywell's current sensors that we call the CSSV1500 amps. This was designed to ISO 26262 safety standards that includes some redundancy in the overall system that provides you just better reliability for redundancy for fail-safe operation. So the CSSV1500 series uses a combination of flux gates and open loop Hall technology. Sensing ranges up to 1500 amps, and the accuracy is 0.5%. It was designed to ACUC, but this can be used in your battery energy storage systems as well. So if you're looking for a system or a solution that provides you just overall better accuracy, better reliability, and redundancy. You can see here it uses several sensing elements in here, and the microprocessor used as a redundant feature as well, so that provides again just better overall system reliability and robustness. Now I'm happy to speak to a current sensor that Honeywell is going to be introducing to the market in Q4. Um, we expect to launch this product into the market in the next 1 to 2 months. We have samples available. We've gone through the full qualification, and we can provide samples to customers. You can start designing this into your different applications, but this will become available for purchase in the next 1 to 2 months. But we're happy to provide these samples for initial evaluation. If you have any questions, you can reach out to your Honeywell sales rep. They'll be able to provide you and support you with anything you need. So the CSN1000 Series was specially engineered for battery energy storage system applications, which is an extension of our battery safety portfolio. It's designed to provide you accurate readings that will enable you calculate your state of charge and overall just meet your overall system performance, optimization, and safety goals. So the CSNE1000 has best-in-class accuracy of up to 0.2% of the readings. This is the best-in-class today. For most all-effect current sensors that are out there today in the market, they are around 0.5%. This 0.2% is best-in-class. It allows you to improve your energy storage measurement accuracy, reduces your system calibration time, and improves or increases your income from your energy storage system spending more time online than having to do several calibration and that you would typically see with a lower accuracy current sensor. So we're pretty excited about this product. Again, is best in class with 0.2% accuracy. Then we have the higher sampling rate of up to 8 kilohertz. Why is this important? The special delta sigma sampling design that this sensor uses just provides you better accuracy with and able to detect DC to DC or DC to AC inverter square wave with high accuracy. With the high sampling rate of 8 kilohertz, you have just better detection of DC to DC or DC to AC inverter or square wave, which is applicable if you're measuring or detecting AC currents as well too. And the robustness of this sensor allows you to adapt to more complex electromagnetic environments. Like we said earlier, in BESS application, where you could have a lot of switching, you could have electromagnetic fields radiated or conducted. This sensor just has a more robust performance that allows it still deliver optimal and superb performance in very complex electromagnetic environments, unlike what you will see with the Shun technology. And the sensor, again, just excellent performance in 2500 amps DC voltage DC environments, and it has a wide bus through all 30 millimeters that just provides you more flexibility for your larger bus bars. And stable performance over temperature, and the sensor is designed for a 15-year life that you would typically see in a battery energy storage system application. So we're very excited about this product. It's an extension of our portfolio today and just allows you to meet your higher system safety goals, better accuracy, reduce your downtime, reduce your calibration time, allows you to generate more revenue and more income for your energy storage systems. So how does this compare to other products that we have in our portfolio today? We've grouped this into 3 groups. We have the low-end solution, we have the mid-end solution, and the high-end solution. The low-end solution here includes the Onwell CSSV Series, which is our open-loop all-effect current sensor, non-contact, and we've grouped that in the same category with the Shun technology from an accuracy standpoint. Typically, you'll see about 2% to 3% in the low-end range. We have also a competitive offering here in this space as well. For the mid-end solution, that ranges up to 700 amps. We have some current sensors that also measure up to 1500 amps here. The accuracy is 0.5% to 1%. So that would be the CSNE700 series, the CSNV500 series. And you can see the difference in accuracy from 2% to 3% to 0.5% to 1%. Now, the CSNE series is best in class, our best offering today for battery energy storage systems with a range up to 1000 amps, higher accuracy up to 0.2%, sampling rate up to 8 kilohertz, again, which is just provides you better detection for DC to DC, DC to AC, square wave or inverter wave, and provides self-diagnostics of overcurrent detection. And the plan for this sensor is to be UL certified, making it ready to go out of the box for BESS systems that typically require UL certification. So we're very excited. Again, we have the CSNV500, CSNV700 that you can also explore depending on your needs and your application. But the CSNE1000 is really the best in class, and we're excited about introducing this product to the market in the next 1 to 2 months. So I hope you've gained a lot from this discussion today and presentation as you think about different current sensing technologies. The key takeaway here is that the all effect sensors, non-contact, are preferred over shunt resistors or shunt technology because they offer galvanic isolation, they have minimal heat generation, they provide better accuracy at high currents across the sensing range, making it more suitable for high voltage and high current environments. So at this point, I will take any questions that you have on current sensing in battery energy storage systems. Thank you.
Well, thank you very much, AJ, for that presentation. There's a lot of different sensing and monitoring that goes into these battery energy storage systems, and it's really interesting to hear about the wide range of products and precisions and capabilities of the sensor range. And I see that we have a few questions coming in, so are you